Uh, uh, Lavanya, I just started the live
Okay,
on
Shubham.
YouTube.
Thank you. Thank you.
Yeah.
Okay, so I guess it is fine. So are you able to hear me now?
It's still cracking.
Breaking.
Ma'am, voice is still breaking.
Is it better in any way? No.
No, ma'am, no, can't hear.
Just scroll the page up, madam, till the time we can read it. What is in a previous slide?
I guess there is some issue with my internet connection. Is it better in any way or is it not at all audible?
It's better now.
No, no, you're audible now.
Okay. Okay. Thank you. Okay. Fine. So, yeah. Okay. So I was telling that if you have a matrix A, which is of the form alpha I, that is, you have a scalar matrix. Okay. And then you are asked to verify if this matrix is similar to some other matrix. Okay. Then you write like this. And then what you get is that P inverse I, P is just P inverse P because you're just multiplying with identity. So you get the same matrix. Now, what is P inverse P? Yeah.
Identity matrix.
So it is just the identity matrix. So you get B is equal to alpha I, which is not the case, right? So it means you cannot have any other matrix which is similar to A if it is of this form alpha times of I. The only matrix which is similar to this matrix is itself. Okay, you cannot find any other matrix which is similar to this. Okay, this is a very important example because I have seen this problem in various form in different problems. Okay, fine. Is this clear that these two matrices cannot be similar, and what is the reason behind it?
Please repeat.
Yeah. See, let us say you are having a matrix A is of the form alpha times of I, where I is the identity matrix. So alpha I will become a scalar matrix. And the question is that if we are asked that if A is similar to any other matrix, okay, even though the trace can be same, determinant is same, rank is same, everything is same, still the matrices need not be similar, will not be similar actually. The reason is that if you write B is equal to P inverse AP, then A is just alpha times of identity. So when you take out this alpha because it is just a scalar, then what you get is that P inverse IP, which reduces to just identity matrix. So it becomes B is equal to alpha times of I, but it is not the case, right? B is not alpha times of I. It is some other triangular matrix in this case. So you see that the only matrix which is similar to A is A itself. No other matrix can be similar to A when it is of this scalar matrix. Okay? Scalar matrices are diagonal matrices where all the diagonals are just the same entry. Okay?
So,
Fine.
Yeah, ma'am,
summarize,
what if
two matrices are similar when they are actually same? There is no other case.
Of course, any matrix is similar to itself. That is an equivalence
that is
relation, right?
Yeah, then why we talk about similar matrices? So is that the statement truth that there is no similar matrix?
The question is about given two different matrices, are they similar? That is the question. Okay?
Can they
I'm
be
saying
similar?
that it is not possible for this particular matrix A that you cannot find any matrix which is similar to A other than this A itself. Okay?
So
Ma'am, can you
A
define
and B are also not
matrix?
equivalent matrices, right?
Sorry, A and B are?
Also not equivalent matrices, right?
No. For equivalence, you don't have this condition. For equivalence, their rank just need to be same. Here you see that rank of A is equal to rank of B, so they are equivalent. They are just not similar. They are equivalent, of course. Okay?
Ma'am, can you define equivalence and similarity in short?
See, for equivalence, instead of P inverse, you have a matrix Q here. Okay, you don't have P inverse, but you have a matrix Q. Remember here I have given this condition for a matrix to be equivalent, that if the rank of A is equal to rank of B, then A and B are equivalent. Okay, but for similar matrices, that condition is not sufficient. You need much more than that. Okay, so here this A and B, they are equivalent because you see that rank of A is equal to rank of B. What is the rank of A and B?
2.
So A and B are equivalent,
2.
but A and B are not similar.
So only
For similarity,
rank is same.
for similarity, determinant has to be same as well, right?
Yeah, the determinant also same in this case, but still you see that A and B are not similar.
No, appreciate. All I'm just trying to check is for similarity conditions, it has to be same order, determinant same, rank same, right? Is there any other parameter to be?
These are just implications for similar matrices. You cannot conclude two matrices are similar with these conditions. Okay?
I agree that. All I'm saying is just want to have a definition of similarity, madam.
Definition of similar matrices is this: two matrices are similar if you can find matrix P such that B equal to P inverse AP. This is the definition of two similar matrices. Okay?
And ma'am, just checking this rank, can we conclude that two matrices are equivalent?
Yes. You can conclude two matrices are equivalent just by looking at the rank. If the ranks are same, then they are equivalent.
Ma'am, if determinant of like A or B is non-zero, then how can we say BA is like similar to AB? AB is similar to BA.
You are asking something different, I guess. We will come to it next. Okay?
Okay.
Fine.
Ma'am, in this case, if B is another scalar matrix with say diagonal element 3, 3, then we can take 3 as a constant outside. Then we can say it is similar.
No, still it should be the same scalar matrix. If you are taking a different scalar matrix, again it's not going to work.
Okay.
So we can say that a scalar matrix would be similar to itself.
Yes, only similar to itself, not to any other matrix. Okay.
Got it. Thank you.
Okay.
And then, ma'am, A is equivalent to B. Then we can say that B is equivalent to A also.
Yes. Okay.
Is it? Okay.
Fine. So how to find this matrix P? Again, this kind of procedure we have already seen. To find this matrix P, you need to express the ordered basis gamma in terms of beta. What is gamma and beta? So you have T from V to V, beta and gamma two ordered basis. A is the matrix representation of T with respect to beta for both domain and codomain. And B is the matrix representation of T with respect to basis gamma for both domain and codomain. Okay. Then A and B are similar and satisfy the equality B equal to P inverse AP, where this P is nothing but the matrix obtained by expressing gamma in terms of the ordered basis beta. Okay. So, yeah.
Ma'am, is it always B is in form of the domain and the codomain is gamma, ma'am? Like, will it?
Yeah. For when you are considering similar matrices, yes, this is what you have to see. A should be expressed with respect to beta for both domain and codomain, and for B for gamma for both domain and codomain. Okay.
Okay, ma'am. And to express P, we have to express gamma in terms of beta, ma'am.
Exactly.
Okay.
And for equivalent matrix, we can have different bases for the domain and codomain.
Yes. For equivalent matrices, actually you see the domain and codomain are different for equivalent matrices. That is why we were having two different bases. But then here you see the domain and codomain are same. That's why we are just having only one basis here. Okay. Fine. So you see, these are the properties of similar matrices, but these do not guarantee that given matrices are similar. It means what? If two matrices are similar, then they have same rank, same trace, and same determinant. These things are implications of similar matrices. But converse is not true. This is very important, that the converse is not true. Okay. If two matrices A and B have same rank, trace, and determinant, that does not imply they are similar. The example we saw is exactly describing this. They are having same trace, rank, and determinant, but still you see that they are not similar. Okay.
For that, we need to solve for PB equal to AP, right? And find like if it's like.
Yeah, if they are similar, then you can find P. But in this case, we know that they are not similar at all. Yeah. Okay. So here is a question. Let A be a 4x4 matrix and B, C all are 4x4 matrices, such that A and B are equivalent matrices and B and C are similar matrices. Okay. If rank of the matrix A is 3, then find the determinant of the matrix C. So given A and B are equivalent. So if A and B are equivalent, what is the property you know?
Same rank is same.
So A and B are equivalent implies that rank of A is equal to rank of B. All right. And B and C are similar implies that, what does B and C similar implies? You have all this condition.
Determinant will be
Same race, same rank, and same determinant.
The condition we need here is about determinant. So let us write determinant of B is equal to determinant of C. Now what is the rank of A and B given to B?
3.
It is given as 3. If rank of B is 3, what can you say about the determinant of B?
It is
Non-zero.
0.
Non-zero.
It is 0. Right? Because it is a 4x4 matrix and it is not full rank, the determinant is 0. Okay, is it fine? Okay.
Yes, ma'am.
Okay, fine. So next question, if A is a 3x3 matrix, if a 3x3 matrix A is similar to the identity matrix of order 3, then A must be the identity matrix of order 3.
Yes.
What do you say?
Yes.
True.
That is what we discussed just now, right? So this is fine. So if A is a 3x3 matrix, if a 3x3 matrix A is similar to a diagonal matrix of order 3, then A must be a diagonal matrix of order 3. Is it so?
Ma'am, need not be the
Not
case.
necessarily.
It is not necessary.
Yeah.
Actually, there is this concept of, I guess during the classes, I have given some specific example also. See, remember that there is a concept called diagonalization. Okay. In this diagonalization, what happens is that you can convert a matrix into a diagonal form. So you can write it as P inverse AP. So where D is this diagonal entries. Okay. So there are several matrices which can be converted into a diagonal matrix. Okay. For example, if you want to construct a diagonal, let us say this is the diagonal matrix. Okay. You can verify that any triangular matrix, okay, let us say this D1, D2, D3, all are distinct, let us say. All are distinct means they are different. In that case, you can see that in fact any triangular matrix with this as diagonal entries, that will be also similar to this matrix. Okay. In the case of all the diagonal entries distinct. Okay. So for different matrices, there are different conditions under which you can find similar matrices for a diagonal matrix. Okay. So this
for the
condition
first matrix, ma'am, the other entries need not be 0, no, ma'am. The D1, D2, D3 one. Yeah.
So this is the diagonal matrix I'm talking about.
Okay. So both the matrices, the other entries should be 0. And the
So
diagonal.
this is the triangular matrix I have considered here.
Okay. And the first matrix is just a diagonal matrix.
Diagonal matrix, yes.
Okay.
Okay. So it is possible that there are non-diagonal matrices which are similar to a diagonal matrix. Okay. That is the concept of diagonalization, in fact. Okay. Fine. Okay. If A and B are similar matrices, then they are also equivalent matrices. Is this true? Yeah. If A and B are equivalent matrices, then they are also similar matrices.
False.
False. Okay. Fine. Okay.
Yeah.
So next,
Two matrices can be similar only if they're square matrices.
first, the very basic condition is that they should be square matrices. Yes.
Okay.
Only for square matrices, similarity is defined.
Okay.
Okay. Fine. Choose the correct options. If determinant of A or determinant of B is non-zero, then AB and BA are similar. Is that true?
Yes. Yes, ma'am.
Okay. So why is that so? Because for example, suppose you consider determinant of A is non-zero. If determinant of A is non-zero, then let us consider A inverse AB into A. Then what is that you get? A inverse A into BA, which is actually just BA, right? So you see that this matrix A itself acts as your matrix P. So what is it you have done? P inverse AB into A is equal to BA. So you see that AB and BA are similar matrices. The same you can do if you are taking determinant of B non-zero also, the similar argument can be done. Okay. So either if determinant of A is non-zero or determinant of B is non-zero, then AB and BA are similar. I guess one student asked this question only. Okay, so this is correct.
Are they not supposed to have
this,
the non-zero determinant of both the matrices?
No, not necessary. See here, I have just used only one condition. I did not use the determinant of B is 0. I did not use that.
Okay. Okay.
Okay, just one of them is enough. Okay, fine. Let us look at the next example. A and B are similar. What about the trace? Are they same?
Yes, ma'am.
No.
Trace is 6 here and trace is 4 here. So you see trace of A not equal to trace of B. So these two matrices cannot be similar. What about this one? The traces are same. But what about the determinant?
Different.
Yeah, so determinant of A not equal to determinant of B, so they are not similar. What about these two?
Scalar matrix.
They are not similar mentioned, so it is true. Right? This is what we just saw before. Okay? So this is a scalar matrix, so it cannot be similar to any other matrix. Okay? Fine? Okay. Okay. Which of the following option is or are true? if A and B are similar matrices, then A inverse and B inverse are similar matrices. Is this true?
True.
Yes.
We have actually done this during the class, I guess, right?
Yes, yes, ma'am.
Okay, so this is fine. If A and B are similar matrices, then A square and B square are similar matrices.
Yes.
In fact, A power n and B power n are similar matrices, we have proved, right?
Yeah.
Yeah. If A square and B square are similar matrices, then A and B are similar matrices.
False.
No, ma'am.
So the counter example is that if you have, let's say, A and this is your A and this is your B. Okay, this is your A and this is your B. The traces are different, but the square of these matrices are just identity. So they are similar matrices, but A and B are not similar, right? So this option 3 is incorrect. Okay. If A and B are similar matrices, then their transposes are also similar. Is that true?
Yes.
Yes.
Yes. Right? Okay. So the next topic is affine subspaces and affine mapping. Okay, what are affine subspaces? Let us consider a vector space V. An affine subspace of V is a subset L such that there exists a V in V and a vector subspace U subset of V such that L you can represent as V plus U. So basically, you have a subspace U of V and then any vector V from V, then V plus U is an affine subspace. That's all. Okay. The very first question about affine spaces is that are affine spaces subspaces of a vector space?
Yes.
No.
Sorry?
No.
Not necessarily.
Affine spaces cannot be, I cannot say, need not be subspaces of a vector space. Okay, they are translations or shifting of subspaces, right? If you remember, for example, any line passing through origin is a subspace, but any line parallel to this line is a affine space. So you see, this is not a subspace. Okay, remember, the very first thing you should know about affine spaces is that they need not be subspaces. Of course, all subspaces are affine spaces, but affine spaces need not be subspaces. Please remember this very well. Okay, so what is that I told you? All subspaces
Affine subspaces to itself.
okay, the converse need not be true. Need not, I'm saying. It may be true in some cases. Need not be true. Okay, any affine space need not be a subspace. Okay, and this in this representation, this vector V need not be unique. Okay, in this expression, this V need not be unique. Actually, we have given some examples where the same subspace, affine space, can be written with various different V's actually. Okay, fine. Now, you see, this V is not unique, but this U is unique. It means what? If you are having an affine subspace, you cannot write this U with, replace this U with any other subspace. Okay, there is only one subspace associated with an affine subspace. Okay, fine. Affine subspaces are just translations of a vector subspace. Okay, so it means what? Every vector subspace is an affine subspace. That is what I told you in the very beginning. And what are the dimension of an affine subspace?
Same as this.
Yeah, so if you have L is equal to V plus U, then dimension of L is same as dimension of U. Okay, so what are all the two-dimensional affine subspaces? To know the two-dimensional affine subspaces, let us consider first of all R2. Okay, in R2, what are all the subspaces first of all? You take a zero subspace and any line passing through origin and the whole space itself. What is the dimension of this space? The zero subspace?
0.
And for this straight line passing through origin?
1.
1. And the whole space R2?
2.
Okay. So the corresponding translations are going to have the same dimensions. Okay. So the translation of these three types of vector spaces are all the possible affine subspaces. What are the possible translations? Any point can form an affine subspace. Any single point. Okay. Either it is zero or non-zero vector. Any single point forms an affine subspace. And any straight line, it need not pass through origin. You take any straight line, okay, that will form an affine subspace. Okay. And the whole vector space R2 itself, of course, is an affine subspace. So again, you know that here the dimension is 0, here the dimension is 1, and here the dimension is 2. Okay. Same way in 3D. First of all, yeah, any question?
Can we define that affine subspace thing for complex numbers also?
In our course, we are not at all considering complex spaces, so let's not worry about it now. Okay. Fine. So first, let us recall all possible subspaces of R3 with the usual addition and scalar multiplication. So in R3 also you have subspaces of, what is the dimension of this subspace, which is just the origin? Again?
Yes, 0.
0. So any straight line passing through origin again has dimension
1.
And then any plane passing through origin, span of 2 different vectors. So for that, dimension is 2. And the whole space R3 has dimension 3. So these are, yeah?
3, correct.
These are, yes, please. No doubts? Okay.
No,
So
no,
these
we
are
just said dimension 3. That's correct.
Someone is saying something, but it's
No,
overlapping.
please go ahead, madam. Go ahead. We were just saying dimension 3. That's all.
Okay, fine. So now you see that you have some translations. Okay, so point affine subspace. So any point if you take, then that is a affine subspace, and it is having dimension 0. Here, if you take V plus a line, a translation of a line. Okay, a translation of a line has dimension 1, and translation of a plane. Okay, a plane translated to another plane. So V plus a plane, it has dimension 2. Okay, and then you see the whole vector space R3 with usual addition is a scalar multiplication. Okay, so note that here in the case of 2D, for this and this you don't have to worry. For the dimension 0 and 2 case, they are very obvious, so you don't have to worry. In the case of dimension 1, so first of all, subspaces are of this form, y is equal to mx, so that it passes through origin. And if you take any y is equal to mx plus c, so these are all general straight lines. So any affine space, okay, any affine space y is equal to mx plus c, what is the corresponding subspace? It is just simply y is equal to mx. Okay, so the same concept comes here as well. In the case of straight line, it is going to be the similar case. And in the case of plane, okay, and in the case of plane, you see these are of the form ax plus by plus cz is equal to 0. So these are the planes passing through the origin. Okay, and if you are translating it, they are going to be plane of this form ax plus by plus cz equal to d. So if you are having any affine space of this form, then the associated subspace you can easily write by making this constant to be 0. That's all. You don't have to do any calculation. Simply make this to be 0. That's all. Okay, we have some example below. Let us see. Okay, before that, let us first see what are addition and scalar multiplication on affine spaces. So you take affine space L is equal to V plus U. How do you add two elements? So you have an element V plus U and V plus U dash. Then the addition is only for the component of the subspace and not for this vectors. Remember, the addition is only for the subspace and not for this vectors. And same way, scalar multiplication is also only for the subspace component and not for this vector. Okay, so the addition and scalar multiplication we are doing only for the component from the subspace and not the vectors. Okay, fine. So now when you have affine subspaces, you can define affine mappings corresponding to this linear transformations. So how do we do that? So let us say you have two different affine subspaces L and L dash. So you define a function f from L to L dash. Okay, so now let us say any vector v in L and the unique subspace U. So it means what? L is equal to v plus U. So you have this representation for L. Now f of v belongs to L dash. So it means what? You can write L dash is equal to f of v plus u dash, where u dash is the unique subspace of W. Okay, remember, if you have L is equal to v plus u, this v can be any element of L. The same, this concept only it is used here. So f of v belongs to L dash. So to represent L dash, it can represent it with any element of L dash. That is why f of v plus u dash, where u dash is the unique subspace of W. Okay, corresponding to this L dash. Okay, now how is this affine mapping from L to L dash defined? It is defined as G from u to u dash, where G of u is equal to f of v plus u minus f of v. Okay, G of u is f of v plus u minus f of v. Only when you define it in this way, we get that this is a linear transformation. Okay, so for this linear transformation, you can actually check that the usual addition and scalar multiplication properties are satisfied. Okay, fine.
Excuse me,
so
ma'am.
When you,
ma'am,
yeah?
Can you please take for this? Can you please take one example?
Yeah,
for
there is
GU?
an example following. Yeah, there is an
Okay.
example following. Okay. So also when you are given a linear transformation, you can also obtain an affine mapping by defining f of, suppose you have t from u to u dash, a linear transformation, then you can define the affine mapping f of v plus u as v dash plus t of u. Okay. So here you are, for this u, you just map it to t of u. That's all. Okay. And v dash is, v and v dash are fixed elements of L and L dash. This is how you define an affine mapping if a linear transformation is already given to you. Okay, fine. So with these properties, let us solve an example here. Let L and L dash be affine subspaces of R3, where L is equal to 0, 1, 1 plus u, and L dash is equal to 0, 1, 0 plus u dash. Okay. Now for this, there is a basis given for u. Okay, and a basis for u dash also. So what is the dimension of u here? So
Two.
what is the dimension of L as well as dimension of u?
2.
2. Okay, and what is the dimension of L dash?
1.
Yeah,
1.
it's 1, spanned by only one vector. Suppose there is a linear transformation T from u to u dash such that 1, 0, 1 belongs to the kernel T and T of 1, 1, 0 is 1, 0, 0. So you are now defined an affine mapping in this way. Now you are asked to check the following options. Okay, which one is correct? We need to check. What is the first thing? You have to first find what is the affine space corresponding to this. What is this L? You need to first of all find. Okay, for this you need to know what is your U. So your U is the span of 1, 1, 0, 1, 0, 1. Right? If your U is this, then how can you write it? Alpha times of 1, 1, 0 plus beta times of 1, 0, 1. So what is your subspace then?
Ma'am,
Yeah?
and how can we say that dimension of u is 2 and dimension of u dash is 1?
How many elements are forming a basis for U?
Okay. 2.
Same thing, how many elements are forming a basis for U dash?
Okay. 1.
Okay.
Okay, ma'am. Ma'am, I have a doubt from 7.1. Please, can you consider this in end of the session?
Yeah, sure.
Thank you, ma'am. I put it in the chat box.
Okay, fine.
Thank
Okay, so now U is equal to span of these two vectors. So it means U is the set of all vectors of this form where alpha and beta are any real number. Okay. Now you can in fact, since everything is given in terms of x and y, okay, let us now write x is equal to alpha plus beta and the second term is y is equal to alpha. Then what is this third term? It is beta. Then how can you write?
X minus y.
Yeah, it is just x minus y. So x, y and x minus y. So this is your u. So if this is your u, then what is your L?
I need to add 1, 0,
Yeah.
1.
Yeah. So you just need to add 1 to the second and third component. So it becomes x comma y plus 1 comma x minus y plus 1. Okay, where x and y is in R. So you can also represent in some other way also. I guess this matches with one of the options, I guess. If I remove option 3. Okay, so option 3.
First one.
First one, x, y plus 1, x minus y plus 1. Yeah. So this option coincides. And option 3 and 4, are they coinciding with this? So to check whether they are coinciding with this, you just have to see whether they satisfy this condition that the third element is the just the subtraction of the first minus the second. So is it satisfying that? You just need to check. It is not satisfying, right? First minus the second component is not the third component. Same way, first minus second component is not the third component here also. So these two options are incorrect.
Hello.
Okay.
Hello.
Fine. Next, we have to find what is your L dash. L dash is simple. You just have only one vector. So L dash is set of all. Yeah. X comma. Yeah.
Ma'am, even first option doesn't satisfy that condition, right?
Yeah, x, y plus 1, x minus y plus 1, right? Exactly coinciding with this.
No, x minus y should be then x minus y minus 1, isn't it?
No, see, that is how we have written x, y minus y, and then you have added 1 to the second and third component. It is L, right? L is 0, 1, plus u. You add this vector to this.
Okay, without the affine. Okay, got it. Yeah, thank you.
Okay. And yeah, this is your u dash. Your u dash is set of all x comma 0 such that x is in R. And what is the vector you are adding to it? You are adding 0, 1, 0. So what is that you will get? X comma 1, 0, x is in R. So do you get such a L dash here?
No, ma'am.
Okay, it is not the case. So you see, this is not an answer for L dash. L dash is of this form. The second coordinate is a fixed number 1. It cannot be any y plus 1. Okay, fine. Okay, so the next question, an affine mapping.
Ma'am, can you please explain L dash again?
See, L dash is, what is your, this is your u dash actually, right? U dash is fine for you, right? This is your u dash. Now for L dash, it is this vector plus u dash. 0, 1, 0 plus u dash. So it means you are adding this 0, 1, 0 to this vector. It means it becomes x, 1, 0. So it means your second and third coordinates are fixed numbers which are 1 and 0. Here it is not a fixed number. It can change throughout R. It means it is not 1. Right? So this option is incorrect. Is it fine now?
Yeah. Good.
Okay. Okay. An affine mapping f from L to L dash is obtained by defining f of 0, 1, 1 plus u as 0, 1, 0 plus t of u. Now, which of the following options are correct? So you see that, first of all, what is the information given to you? Let us see. So the information given to us is, you have 1, 0, 1 belongs to kernel of t. What does that mean?
T of 1, 0, 1 equal to 0.
It means t of 1, 0, 1 is 0, 0, 0. Now, what is t of 1, 1, 0?
1, 0, 0.
1, 0, 0.
1, 0, 0.
Yeah. So it is 1, 0, 0. So now you see that you are having the mapping for the basis elements. So these are the basis elements for u. Now you are asked, you are given that f of 0, 1, 1 plus u is 0, 1, 1 plus t of u. Okay. Now you have to verify which of these conditions are satisfied for f. So f of x, y plus 1. So here this is an element of, f is an element of L. And you know how does an element of L looks like. So which one should be, which one is matching with this element? You can eliminate the other options first of all.
First one matches. Option 5.
Option 5 and
Option
this also is coinciding, right?
Yes.
So these two we can eliminate first of all. And now you have to verify whether this option 5 or option 8 is correct. Which one is correct? We need to check. Okay. So now take any element of.
Ma'am, can you repeat the step, ma'am? I didn't understand.
See, what I have said is that first of all, F is a map from L to L dash. So F of, you should have an element of L here. And you know how does an element of L looks like. So here you should have an element of this form. So I have just not excluded the other part where the element is not from L. Is that
Okay.
fine now?
Yes, ma'am. Yes.
Okay. Now you have to see what is this T of U. Now U is any element of U. Now what is the transformation here? You know that. Now you see that U is x comma y comma x minus y. Right? Now what is T of x comma y comma x minus y for any x y x minus y? So it means you have to first of all write this x, y and x minus y in terms of this two. How can you write?
x101
X times of 101
plus y times of
plus y times of
110.
Is it correct? I don't think so.
10. Sorry, 1.
0, 1 minus 1.
So what is your alpha and beta? Actually, I need to find. So these are the basis elements for you, right? 110 and 101. So let us write alpha here and beta here. Here 110 is here. So alpha plus beta, then beta and then alpha. So your beta is y and alpha is x minus y. Okay. So you get x minus y times of 101 plus y times of 110. Is this fine? Is this fine up to this step? Yes or no?
Yes,
okay.
yes.
Now what is your T of x comma y comma x minus y? So you have to use this representation. So T of x minus y times of 101 plus y times of 110. So when you split this, you get x minus y times of T of 101 plus y times of T of 110. Now what is T of 101?
0.
So this is the 0 vector and this is your y times of 110.
100.
100. So it is simply y comma 0 comma 0. So your T of x comma y comma x minus y is y comma 0 comma 0. Okay. Now, so now what is your f of 0 comma 1 plus u, which is this one, x comma y plus 1 comma x minus y plus 1. Now how can we express this? So this means f of x comma y plus 1 comma x minus y plus 1 is given by your vector 0 comma 1 comma 0 plus this vector y comma 0 comma 0. So which is y comma 1 comma 0. So which option is coinciding with this?
Fifth.
Okay. Is it fine? So what is that we have done here? So here they have written this as f of 0 comma 1 comma 1 plus u. 0 comma 1 comma 1 plus u. What is the u we have considered? This is the u we have considered. This is your u, right? And your u plus 1 I have written here. X, y plus 1, x minus y plus 1. Okay. And this they have defined as 0 comma 1 comma 0 plus t of u. And t of u we have found it as y comma 0 comma 0. And so we have obtained it as y comma 1 comma 0. Is it fine for everyone? Yes?
Ma'am, can't we just say that
because the L dash form we anyway found out, right? X comma 1 comma 0. So any vector after the mapping should be on that form. Can't we say
Yes,
that?
that also can be done. This so straight away you can write like this. But since I wanted to give you an idea of how this affine mapping is coming into this picture. Otherwise, you can simply look at L dash and say this is what is the element of L dash. Exactly, that is what you should do in exam. But for you to have an idea about affine mapping, for maybe it can be useful for some other problem also. So I have given you the complete explanation here. Okay.
Sorry, I didn't get that, ma'am. Can you?
Which one?
The shortcut that you are saying now.
There is nothing that this belongs to L dash, right? This element should belong to L dash. Already we have found the L dash. What is your L dash? It is of this form x comma 1 comma 0 where x belongs to R. And which one satisfies that? This, not this.
All right.
Okay.
Thank you. Yes.
Fine. Okay. So, what is the next question here? Just have a look. So you need to find, you are given, this is a very straightforward question. I already told you how to find an answer if you are given an affine subspace like this. So you are given affine subspaces. What is the dimension of these affine subspaces?
3. No, it's 2.
R3, same as R3.
Yeah, I told you that they are of this form, AX plus BY plus CZ equal to D. Then what is the corresponding subspace?
Ax plus by plus c is equal to 0.
Right? So now for L1, what is the corresponding subspace?
Option 3.
Okay. Same way for L2, what is the corresponding subspace?
Option 2.
Option?
2.
2. Okay. And what about this one? They are asking what is W1 intersection W2. How do you find what is W1 intersection W2? You have to solve this system of equations. So you have 2x plus y plus 2z equal to 0. And you have x plus y plus 2z equal to 0. It means what? X plus y plus 2z. I'm just splitting the 2x into it. This is 0 and this is 0. So what does this mean?
X plus
Your
x
is 0. X
okay,
is 0.
Your x is 0 means y plus 2z is 0. So this intersection definition is fine.
Why fourth option is not correct?
What is fourth option? I did not know.
How did you write ax
No,
plus by plus cz equal to 0?
See, this is what I told you. If you are having, first of all, an affine subspace like this, so for any affine subspace of this form, the corresponding subspace, remember a subspace is a this kind of a subspace is a plane. So a plane passing through origin. So 0 means that it is passing through origin. So only if it is 0, then it can be a subspace. So if it is 1 here, it is not a subspace. Okay, sorry, it is not a, it is not a subspace. It means it is not a plane passing through origin. That is why this is not a subspace corresponding to this L1 and L2.
Oh, okay.
Okay, ma'am.
How will you add any vector to this subspace?
Yeah.
How to add any vector to this subspace?
Okay, the addition of the vectors already is defined to you, right? So here you know that now this L1 is some vector V plus a vector from this W1, this particular W1. So you take this L1 is equal to, suppose you have two elements, V plus a vector from here, which satisfies this condition x plus y plus 2z. Maybe I can give you something like 2, 0, minus 1. I guess this satisfies this condition. Okay, this is one vector and the other vector is V plus, maybe I can take 1, 1, minus 1. Okay, so now these two vectors are elements of L1. Now how do you add these two elements? So this is, let us say, L1, L2. Now L1 plus L2 is simply V plus the sum of these two elements alone. Okay, so 3, 1, -2. Okay, this v you don't disturb. Okay, the same way scalar multiplication also. Fine.
But we can have different v for this. You said that v
Yeah,
can
the v can be any element of L1. This v can be any element of L1. You can take any any v which satisfies this condition. Okay.
So you have for L1 there is different v and for L2 there is different v.
Yeah, you can choose any v.
So
Okay.
you do not add both v.
Yes, those v's you don't add. That's all. This v is just any element of L1. Okay. Fine. Okay. So the next topic is
one question here. So here they have given affine subspace and they're asking for vector subspace. So we are saying that only equal to 0 would be the right ones. But whereas if they have given vice versa, where if they have given the vector subspace and they ask for affine subspace, that equal to could take any values.
Yes, that equal to can take any non-zero value as well as the 0 itself.
Yeah. Okay. Yeah. Got it. Yeah. Thank you.
Okay.
Ma'am?
Yeah.
I have that previous question.
Okay.
Yes, ma'am. Linear combination of bases 110, 101, ma'am.
Yeah. What is the doubt here?
We write x, y, z in linear combination of 110, 101.
Yes.
Scroll down, ma'am.
Here, this
yes,
one?
Yeah, yes, ma'am. X, y, x minus y.
Yeah. What is the doubt in this?
Alpha plus beta, beta alpha.
Now you just equate it coordinate wise. The first coordinate x is alpha plus beta, your y is beta, and x minus y is alpha.
Okay.
Right?
Yes,
so it means what is your alpha plus beta? It is simply
X.
Sorry, you don't have to worry about what is alpha plus beta. You just need alpha and beta here, right? So alpha is y and alpha is x minus y and beta is y. So you have just substituted, instead of alpha you substituted x minus y and beta is y. That's all.
Okay. Okay.
Okay.
Okay.
Fine.
Thank you.
Okay. So we are moving to the next topic. So the next topic is dot product in Euclidean spaces. So you know dot products very well. So you take any two vectors in R1, you just do the coordinate wise multiplication and then add them. Okay, it is very simple. And what is the length of any vector in Rn using the dot product? U1 square plus etc. U square. And which is, in terms of dot product, it is actually u dot u square root. Right? So square root of u dot u is the norm of any vector. Okay. And what is the angle between two vectors? How do you identify it? It is cos inverse of u dot v divided by square root of u dot u into v dot v.
So here u dot v is inner product. No?
So this is just dot product. The next topic is inner product. Okay.
Is length of a vector and distance of a vector is both same or different?
See, length you talk about one single vector, distance you can talk about two different vectors. If you are talking about distance of one particular vector, in general they usually mean the distance from the origin. That's all. Okay.
Okay. Okay. So in that case, like if they ask for two different vectors, so distance formula means we'll usually use our old distance formula, right?
So distance between two vectors, it is u minus v, norm of u minus v.
Okay. Okay. Yeah. Thank you.
Okay. Fine. Now let v equal to R3 be the inner product space with usual inner product if theta is the angle between this vector and this vector where this ABC satisfies this condition. That means what? You have, let us say this is V1 which is 14, 11 and 5 and V2 is A, B and C. Your V1 dot V2 is 14, 11, 5 dot A comma B comma C. What is that? What is that?
14A 7B plus 5C.
Okay, and that is given as 0. Okay, now they are asking us to find the value of cos theta. Now what is the formula for cos theta from this above formula? Cos theta is equal to v1 dot v2 by square root of v1 dot v1 into square root of v2 dot v2. But what is v1 dot v2 given to be?
0.
Okay, fine. So if v1 dot v2 is given to be 0, then cos theta is 0. But then why do you need this condition? Can you tell?
Denominator.
Yeah, to make sure the denominator is non-zero.
Be 0.
Yeah. So this condition guarantees us that this denominator is non-zero. Already we know that this part is non-zero because it is explicitly given. To make sure that this part is also non-zero, this condition is given here. So now you know that the value of cos theta is 0. Okay, fine. So the next topic is inner product space.
Ma'am, the angle will be 90 degrees, no ma'am?
So here they are just asking the value of cos theta. Yeah, if you want to specific write the specific value of theta, yeah, you can write pi by 2 or 90. Yeah. Okay. So inner product, an inner product on a vector space V is a function V cross V to R satisfying the following conditions. So the first condition is called positivity. Second condition
bilinearity.
And fourth together is called bilinearity, and the third condition is called
Symmetry.
Okay. Now, if all the conditions are satisfied, then we call this as an inner product on a vector space. So a vector space together with an inner product is called an inner product space. Okay. Now you are given a function from V cross V to R, where V is a subset of R2, defined by f of V comma W in this specific way. Okay. Now, first option is that it is given that it is symmetry. Symmetry means what? How do you check symmetry? You have to check
W is equals to f of WV.
F of V comma W equal to f of W comma V. This is what you need to check. So f of V comma W is already given to you. So let us simply write whatever is given. Okay, and what is f of W comma V?
W1 square V1 square
plus
W1 into V2 square plus W2 square V1.
Okay, so here what happened? This term is coming as a second term, and this term, coming as a third term here, and the third term is coming as the second term. So nothing has changed. So this is true in fact, right? We have verified and it is true, right? Yes or no? Yes, right? So we have to verify and it is true. And what about the positivity? For positivity, you need to check f of V comma V is positive for any V, any non-zero V. You take any non-zero V and verify that. So it means what happened? What is f of V comma V? It is V1 power 4 plus V1 square plus V2 square V1. Okay, so it is actually V1 power 4 plus 2 times of V1 V2 square. So this is what is f of V comma V. From this can we conclude that it is positive? Only if there are square terms and powers of even numbers, then we can say, but here there is something.
V1 mom, yes.
So whenever you have an unsure condition, then it is possible that it is not correct. Whenever sometimes you are not able to conclude from this, then it is possible that it is incorrect. So you need to find a counter example. Remember, your V is a subset of R2. So your V is an element of R2. So let us try this one. You need to somehow say that this is not positive. So you have to make this a negative number. So let us try with minus 1 comma 1. What happens to f of V comma V when V is minus 1 comma 1?
1 minus 2, 1. Sorry, 1 minus 2.
Which is a negative number. So is the positivity condition satisfied here?
No.
No.
So is this an inner product?
No.
No.
Okay, F is not an inner product. Okay.
Ma'am, even first one, does that look same? Because I feel it's different.
See, this second term is nothing but W1 V2 square.
W1 V2.
Two
Okay,
terms are
okay.
same.
Okay,
Same
okay.
way, two terms.
Okay, okay. Yeah, got
One
it.
W2 square. Okay.
Okay, got it. Yeah.
Fine. Okay, so the next thing is that norm on a vector space. A norm on a vector space V is a function from V to R which satisfies these conditions. So the first one is the triangle inequality. And then you have this condition that norm Cx is equal to mod C times norm X and norm X is greater or equal to 0. Okay, and also norm X is 0 if and only if X is 0. Otherwise, the norm cannot be 0. Now, a norm can be induced by an inner product. If you are given any inner product, then you can define an inner norm by simply defining its square root of inner product V comma V. So, for example, suppose you have seen some other inner products, right? Maybe suppose here you have V1 square and W1 square, then it may be an inner product. Then from this inner product, you can define a norm. Okay, just by defining it as norm V equal to square root of inner product V comma V. Okay, fine. Consider a vector A1, B1, C1 in R3. Okay, so here A1, B1, C1. Which of these are possible candidates for a norm? Okay, what about the first one? So the first one, does it satisfy all? Does it satisfy all this condition? In fact, this is what? This is the usual inner product.
Yes, ma'am.
Right? This is the usual dot product. So and we know already that this satisfies a norm. So you don't have to verify anything. We have this is a very familiar one. We know this is true. What about option 2? A1 minus B1. Does it satisfy this norm greater or equal to 0 condition?
No.
Suppose you are having some vector like 0 minus 1, or 0 plus 1, 0 also. Then A1 minus B1 means it is simply minus 1. So this condition, the positivity fails. What about this one?
How A1 minus B1 works?
A1 minus B1, what? This is your A1, B1 and C1. What is A1 minus B1 then?
Okay,
Minus 1. Okay, it is not satisfying this condition. What about option 3? Suppose you are having something like this. Then what is A1 plus B1 plus C1?
Minus 1.
Again, it is not satisfying positivity. What about this one? Maximum of A1, B1, C1. You can take the same. You can take the same element also. What is the maximum of this?
It will fail the 0 condition.
Zero. Maximum is 0. But is this a 0 vector?
No.
No.
It is 0, but the vector is not 0. So this condition fails. It is non-zero vector for which the norm is 0. So this condition fails. What about this one? Minimum of A1, B1, C1. Again, for the same vector, you can take the minimum and you see that it is negative. So the positivity condition fails. Okay. What about maximum of modulus of A1, modulus of B1, modulus of C1?
It is okay because modulus makes the negative one is possible.
So this condition, these conditions are obvious, and also this condition you can verify because for modulus, this triangle inequality is true, we know.
Correct.
So since modulus satisfy the triangle inequality, you can also derive that this is satisfying the conditions of a norm. Okay.
Can you give an example when triangle inequality fail?
Can you please be louder?
Any example, any condition with triangular inequality fail?
Any example where triangle inequality fails?
X square plus y square.
Yeah, you can take without maybe this itself. What about this one? Does the triangle inequality satisfy for this one? A1 minus B1 if you are taking. So norm of any two vectors if you are taking, I don't think the triangle inequality will be satisfied for this itself. Okay. You take any two vectors and define the norm by just first coordinate minus second coordinate. I don't think the triangle inequality is satisfied in that case. Or this one, option 3 also.
Probably asking when only triangular inequality fails. Maybe that's what it is.
Only triangle inequality fails. I have to check that. I'll look into it and maybe I'll tell
X square plus y square satisfies that.
Which one?
Plus y square defined by x y. Yeah.
X squared plus, so norm of x comma y defined by x squared plus y squared. Maybe.
Side will have 2xy and the other side will only have like.
Yeah. Okay. Okay, fine. So the next question here is that let inner product denote the standard inner product, that is the usual inner product. Which one of the following option is or true for the vector gamma from R2 such that alpha comma gamma is 4 and beta comma gamma is 8, where alpha and beta are given. So let us write gamma as Z1 comma Z2. Okay, and your alpha and beta is already given. So you are given alpha comma gamma inner product is 4, the usual dot product. So you have 3 comma 1 dot Z1 comma Z2 is 4. So it means what? 3Z1 plus Z2 is equal to 4. Okay, and then you have beta is 6 comma 2. So 6 comma 2 dot Z1 comma Z2 is 8. So if this is 8, then 6Z1 plus 2Z2 equal to 8. Now this actually reduces to only one single equation because both are multiples of each other, right? Just if you multiply the first equation by 2, 1 into 2, you get the second equation, right? So you simply have one equation, 3Z1 plus Z2 is equal to 4. So now it depends on what is your t. So if you take Z2 is equal to t, or since you have different format here, maybe I will take Z1 equal to t. So if Z1 is equal to t, then what is your Z2? 4 minus 3t.
3t.
Okay, so you see that your gamma is set of all t comma 4 minus 3t, where t is in R. Okay, so this option is incorrect. There are infinitely many such vectors which satisfy the property of gamma. Is that true?
Correct.
Yeah. So you have infinitely many vectors here. Gamma is unique in R2. Not correct.
No.
Any vector of this form? Yes, it is correct. 1 comma 1. Does it satisfy this property? 4 minus 3t. 1 comma 1.
Yes.
Does 1 comma 1 satisfy this property?
Yes.
But it is not the only vector, right?
Yeah.
If they have given one of the vector, then it's fine. But it is given the only vector, so it is incorrect. Okay? Fine. So next we can move to week 8 topics. So here the very first thing is about orthogonal vectors. When do we call two vectors to be orthogonal? Two vectors are said to be orthogonal if inner product u comma v is 0. Consider two orthogonal vectors a and b in R2. So if a plus b and a minus b are orthogonal, then choose the correct option. So you are given that this is a condition for orthogonality. Now you are given this problem where a plus b and a minus b are orthogonal. It means what? Inner product a plus b.
A plus b and a minus b inner product
0.
equals 0.
So now you can split this. You know the properties of inner product. So using properties of inner product, you can split them. This is what you get. Now because of symmetry, this 2 will get cancelled, right? Because of symmetry, you can cancel these two terms. Inner product a comma b is same as inner product b comma a. So this two term will get cancelled. So what is remaining? Inner product a comma a minus inner product b comma b is equal to 0. Or you can write it as inner product a comma a equal to inner product b comma b. Which means norm a square equal to norm b square. and that implies norm A equal to norm B. Okay.
Option 1.
So which of the following option is correct? Which one is matching option 2?
Option 1.
Why option 1? You don't know whether it is equal to 1.
You don't have a
just
value. Yeah. Option 2.
How did we express the second step, ma'am? A, comma, M.
This one?
Yes, ma'am.
It is simple property of using inner product. How we are doing this? So if you want to do it step by step, then you have to do it like this. So first you do this with only one value. So inner product A comma B with A, and then you have a minus inner product A plus B comma B, and then now this addition you would again do with this value A comma A plus B comma A, and then this addition again you split and write it in this way. That is I have written straight away. Fine. This is just a basic property of inner product only. Okay. So what are orthogonal set of vectors? An orthogonal set of vectors of an inner product space V is a set of vectors whose elements are mutually orthogonal. It means what? Inner product Vi Vj is equal to 0 for all ij in this set where I not equal to j. This is important. I not equal to j means they are mutually orthogonal. Okay, you take any two vectors from this set, they will be orthogonal. That is what is orthogonal set. And orthogonality implies independence. This is a very, very important property. Okay, that if you have an orthogonal set of vectors, then it will be always linearly independent. Okay.
And orthogonal vector only exists for inner product space or any vector space.
Yes, so orthogonality concept is defined only when you have an inner product space. Otherwise, it is not defined. Okay. So what is an orthogonal basis? If you have an inner product space and you have a basis consisting of mutually orthogonal vectors, then you know that that is an orthogonal basis. What is a very easy example for an orthogonal basis for Euclidean spaces?
Standard order basis.
The standard basis. Okay. So remember that basis is a maximal linearly independent set and orthogonal sets are linearly independent. So it means what? If you are having a vector space of dimension n, then the orthogonal basis has maximum n vectors. Okay, or not maximum, it should have exactly n vectors. Okay, fine. What are orthonormal sets? It is an orthogonal set, and also another condition, norm of each vector is 1.
Ma'am,
Okay.
The previous point. So
Yeah.
in R3, we should have 3 orthogonal set of vectors, ma'am. Is it like
Yes.
that?
For an orthogonal basis of R3, it should have 3
basis.
orthogonal set of vectors.
Yes, ma'am. If it is just an orthogonal set, then it can have 2 or 1 also.
Maximum for any orthogonal set in R3, maximum only 3 elements can be there.
Okay. Ma'am, and vector itself can it form? It will form an orthogonal set, right?
Which one?
A single vector, ma'am.
A single vector? Yes, orthogonal you can do. Yeah, you can consider it as an orthogonal.
Ma'am,
Yeah.
if two vectors, their dot product is 0, then they are orthogonal.
Yes.
But they form basis. Are they form basis?
If it is in R2, yes, it forms a basis.
But in R3, it is not.
No, it forms a basis for some subspace. That's all.
Okay.
Okay.
Ma'am, why is single vector orthogonal?
See, a non-zero vector is linearly independent, we are saying, right? The same concept for orthogonal, but it does not make sense actually to talk about orthogonality of one single vector.
Yeah.
Yeah, it does not, it is not at all having any significance. But yeah, by definition, if you say yeah, but it does not have any meaning actually.
When it's defined, it's saying it's I not equal to j itself. So I don't know if you can say one.
Yeah, there are no other vectors to compare. So
Yeah.
So yeah, it is something, it does not have any meaning, so don't worry about it. Yeah. Okay. Orthonormal basis. An orthonormal basis is an orthonormal set of vectors which forms a basis. Okay. An orthonormal basis is an orthonormal set, means each vector has norm 1 and also that set should form a basis. That's all. Okay. So each vector has norm 1 and it is the maximal orthonormal set. Yes.
If we only have orthogonal set, then how can we make it a basis?
Yes, for that only. Okay. So if you only, how do you
What should we check for that, or what should we do?
You just have to look at the dimension. Suppose you are having a vector space V and the dimension of the vector space is n. Then you need n orthogonal vectors for forming a basis, orthogonal basis. That's all.
For R3 we need 3 only.
Yes, R3 we need 3 vectors.
Okay.
Okay. Obtaining orthonormal set from orthogonal set, what do we do? If you have an orthogonal set, you simply divide each vector by its norm, then it becomes an orthonormal set, right? So take any vector, divide by its norm, then it becomes a unit vector. It means what? The norm of this vector is simply 1. Why is that? You can write it in this way, and hence it is 1 for any non-zero vector. Okay, so if you divide any vector by its norm, it becomes a unit vector. Okay, fine. Choose a set of correct options. Suppose beta is equal to V1, V2, Vn is an orthogonal basis of an inner product space V. If there exists some V in V such that inner product V comma Vi equal to 0 for all these basis elements, then V equal to 0. Is that true? Yes?
Yes.
Why is that so?
0 is orthogonal to every vector.
No, they are first of all not saying that the vector is 0. They are saying if inner product V comma Vi equal to 0 for all I, then you have to prove that V equal to 0.
Says then V equal to 0.
Yeah? Why is this V 0?
V cannot be 0. V can be
No, it need not to be true, right? It's basically all are orthogonal.
No. Hold on. See what? So now, first of all, this is a basis, correct?
It's a basis, right? Yeah. You can take a linear
basis,
combination of.
you can write it as a linear combination of these entries, right? Now it means what? This is summation I equal to 1 to n alpha I Vi for all I. Now what happens? Now if this element is orthogonal to all these elements, means now it means, first of all, you don't even have to look at all these things. It means what?
It has to be
V1, V2, Vn, comma V. This forms an orthogonal set. Is this possible?
Yes.
Is this possible? They are given that this is a basis. Maximum n elements only can be there. Now you are having an n plus 1 element orthogonal set in a space of dimension n. Is this possible?
But we are not having n plus 1, right? I is up to n.
Yeah?
Yeah,
this is up to n, and then you are having one more element, non-zero element.
Where does it say, ma'am?
Inner product V comma Vi equal to 0 for all I means what? It is orthogonal to all these elements, so it forms an orthogonal set, right? Is it possible?
Understood, ma'am.
Okay, so you have n plus 1 orthogonal set, which is not possible for a space having dimension n. Here dimension of your V is n. So it cannot have an orthogonal set of n plus 1 size. Okay, is it fine?
This V is outside the beta, is it? The V.
Yeah, this V is not an element of beta. Yeah, some V.
Okay. So basically, what it tells is there is a basis there, and you are adding another V.
Yeah.
Or sorry,
And
another V is orthogonal to all of those. So basically,
yes,
it's another orthogonal, which is not possible.
Yeah.
Okay.
So for any orthogonal set will have only in vector.
Louder, please.
Any orthogonal set will only have in vector and as dimension of their domain.
Yes, maximum n vectors. It can
Either,
have less for a basis. It can have maximum only n vectors. Okay. Okay, fine. So option 2, there exists an orthonormal basis for Rn with standard inner product. Of course, you know that, right? The usual inner product, the standard
First
basis.
is wrong, right?
Which
First
one?
is right.
First option 1 is right.
Right.
It is right.
Okay.
And option 2, you know that standard basis is an orthonormal basis for inner product for Rn with the standard inner product, right? And option 3, if PW, sorry, I did not start projection yet. Maybe I will come back to this this option alone after I talk about projection. These two options we will come back after discussing projection. Okay.
Yes.
Okay. What is the importance of an orthonormal basis? If you have an orthonormal basis and you can write V as C1 V1 plus C2 V2 plus Cn Vn, then you know that this Ci's you can easily compute using this formula. I wanted to use this property only here. Okay. Do you understand why I was writing this?
Yeah.
Now you know that this alpha is nothing but inner product V comma Vi from this property. This alpha is nothing but inner product V comma Vi. But what do you know about inner product V comma Vi? What do you know about inner product Vi?
0.
So alpha is 0 for all I. It means your V is 0. This is the argument I wanted to do. But yeah, there is another way of doing it also. Okay. So from
this
this
only for orthonormal basis, ma'am.
Can you explain option 1 once again?
So in case of orthogonal, maybe you just have one more norm here. That's all. But anyway, you can have the similar way of telling this. Okay.
Okay. So for now, should we just consider it? If at all we are given a set of vectors, orthonormal set of vectors, and we can write it as a linear combination, then we can find the constants. No?
Yes, exactly. The constants you can find by just using this. Someone asked some question. What was that? Okay, fine. So this I'm explaining it in the next example. Consider a basis V1, V2, V3 of R3 with usual inner product. Suppose your V is an element defined in this way, x comma y comma 3x plus y by 5. And you are writing this V as C1 V1 plus C2 V2 plus C3 V3, where C1 plus C2 is given as 4. What will be the value of C3? First of all, what is the observation about your V1, V2, V3?
They are orthogonal.
Yes, you see that inner product V1 comma V2 is 0, inner product V2 comma V3 is 0, and inner product V1 comma V3 is 0. Right? It means what? This forms an orthogonal set. If this forms an orthogonal set, then what can you say about inner product V comma Vi? You can see that it is C1 V1 plus C2 V2 plus C3 V3 orthogonal basis. Okay. Okay. Sorry, why I'm writing everything. So it is simply, you can write it as the value is Ci is inner product V comma Vi. Okay. So now you can write what is your Ci, inner product of this vector x comma y comma 3x plus y by 5 dot, what is your V3?
0, 0, 2.
So which is 3x plus y by 5 into 2. So this gives you the answer. Okay. And if you have to find what is your x and y, that is why they have given what is the C1 plus C2. So they have given C1 plus C2 is equal to 4. So you can write C1, you know that it is inner product of this vector with this. So you have x plus 2y, and you have C2 is equal to 2x minus y. And it is given that x plus 2y plus 2x minus y is 4. Okay, so you have 3x plus y is given as 4. So now you can substitute it here. So 4 by 5 into 2. So 8 by 5 is your answer. Okay. Is it fine? Okay.
Yes, ma'am.
So choose a set of
correct. Can you scroll up, ma'am? One second.
Yeah.
So how did you get the 3x plus y by 5? Huh?
This one?
Yes.
If you do the dot product, usual dot product, what is that you get? The first two terms are multiplied with 0.
Okay.
And this one, you see that it is just multiplied with 2. That's all.
And how did you get the equations is equal to 4, ma'am?
Because it is given that C1 plus C2 is equal to 4.
Okay.
Okay. Fine. Okay. Choose the set of correct statements. In an orthogonal set, the norms of all the vectors are equal. Is that correct?
No, ma'am.
It is just an orthogonal set.
Yeah.
So it need not be same, right? If in an orthogonal set, the vectors are linearly independent.
Yes, ma'am.
So this is obviously wrong. If the columns of an n by n coefficient matrix A comprise the individual vectors of an orthogonal set in Rn, then there must be a unique solution of the system Ax equal to B. What do you say?
Yes, ma'am.
Yes, ma'am.
Because if they are orthogonal, then you know that they are linearly independent. So if the columns are linearly independent, you know the matrix is invertible. So if the matrix is invertible, the system has a unique solution, right? So this implies linear independence, and linear independence implies A inverse exists, and A inverse exists implies the existence of unique solution. Okay, fine. So this is correct. And here they are saying no solution, so this is wrong. The determinant of a square matrix formed by a set of orthogonal vectors in Rn is 0. So you have, it is non-zero, right?
Yes, ma'am.
Because if you have the same argument, if you have orthogonal set as a matrix, square matrix, then what happens? The columns or row are linearly independent, so the inverse exists. It means the determinant is
non-zero.
Non-zero. Okay. A set of n vectors can never form an orthogonal basis of Rn minus 1.
Yes, true.
Correct.
Okay, fine. Okay. Consider the system of linear equations. So this is the system given to you. Number of solutions of the above system is. What do you say?
Excuse me, madam.
Yeah.
Question number 7. The correct statement would be a set of n vectors can form an orthogonal basis for n minus 1. Is that correct?
So the correct statement, if you want to say, a set of
n
minus 1 orthogonal vectors.
Yeah.
This forms a basis for
Rn minus 1.
Yeah.
Correct.
Okay, so now let us write the matrix form.
Solution is one unique solution.
Yeah. What is the reason behind it?
These are orthogonal.
Ma'am, determinant can we check, ma'am, if it is non-zero?
Yeah, determinant you can check, but here the property is something easier. What is R1 dot R2? 2
0.
minus 2, which is
0.
0. What is R1 dot R3?
0.
Again, it is 3 plus 15, sorry, plus 12 minus 15, which is 0. And what is R2 dot R3?
Again 0.
6 minus 6, 0. So R1, R2, R3, they are orthogonal. It means the rows are linearly independent. If the rows are linearly independent, does this system have a unique solution?
Yes.
Yes, ma'am.
So you know the number of solution of the above system is 1.
Okay. Ma'am, how did you get the property, ma'am? R1 into R2 is equal to 0, then is it linearly independent?
What does this mean? This means that R1, R2, R3 are orthogonal.
Yes.
So if they are orthogonal, they are linearly independent, right?
Okay. Yes.
Ma'am, how orthogonal set and orthogonal basis are different?
Orthogonal set, for example, if you consider 1, 0, 0 and 0, 1, 0, this is an orthogonal set. And if you add another element which is 0, 0, 1, now this is an orthogonal basis.
And can
Okay.
orthogonal set have more than n vector?
Any orthogonal set?
Can have more than n vector?
No. No. If the dimension is n, then it cannot have more than n vectors. Okay?
But it can have, right?
No, just see what is the property of linearly independent set of vectors first of all. Can a space of dimension n can have more than n linearly independent vectors?
Okay,
No,
it cannot be mutually. Okay, yeah, mutually if you go, yeah.
Okay. Okay, fine. So what is the next question? Let A be the coefficient matrix of the above system of linear equation. This is the system they are considering. Now, which one of the following is true for the matrix AA transpose?
It will be a scalar. Sorry, it will be scalar and upper lower triangle.
Yeah, actually the statement is coming somewhere next.
Transpose, yeah. Orthogonal.
Yeah, it is here. See, the rows of a matrix A are orthonormal if and only if AA transpose is equal to identity. Okay, and if they are just orthogonal, then AA transpose will be some scalar matrix. Okay, so in this case, your AA transpose will be some scalar matrix because they are just orthogonal, not orthonormal. So what is the answer? It is a scalar matrix. It is a diagonal matrix. It is a lower triangular matrix. It is an upper triangular matrix. Okay.
Well, for any matrix, if A and A transpose is identity matrix, then it will be orthonormal matrix.
Sorry, can you repeat?
For any matrix A, such that A into A transpose is identity matrix, then it must be an orthonormal matrix.
Then yeah, then you know that the rows are orthogonal, but you are asking something else, I guess. What is it you are asking? Please ask first.
For any matrix, if A and N transpose is equal to identity matrix, then it must be an orthonormal matrix.
You also need A transpose A equal to identity. The other way around also you need. Here you see the columns are not orthogonal. Okay. You need both A transpose equal to A transpose A equal to identity. Only when both conditions are there, then it will be orthogonal. Okay. Fine.
Ma'am, how did we check the options, ma'am? I didn't understand.
Ma'am, is any diagonal matrix also a lower triangular and upper triangular?
Yes, you can consider it. Only condition for a lower or upper triangular matrix is that the below diagonal or above diagonal part is 0. That is satisfied for a diagonal matrix. So any diagonal you can consider it as triangular matrix as well. Okay. So without calculating, if you want to check, you can check. Otherwise, you can simply calculate the values also. So
it is not a scalar matrix, maybe.
Why it is not a scalar matrix? See what is happening here. So 1 into minus 2. So when you do this multiplication, what happens here? R1 dot R1. What is R1 dot R1? 1 plus 4 plus 3, which is
9. No?
Plus 4
9.
plus 9.
4 plus 9.
And then R1 dot R2 is 0 and R1 dot R3 is 0. And then R2 dot R1 is again 0. And then what is R2 dot R2? So this is R2 into R2 again. So you
4 plus 1, 5.
How are you?
Yeah, it is
The
not
first element.
Sorry. It is just a diagonal matrix. Yeah.
The first element is 1 plus 4 plus 9, right?
Yeah.
That's 14.
1 plus 4 plus 9. Yeah. Then 13. 14. 1 plus 4 plus 9. Yeah.
Ma'am,
And then
instead of multiplying, you're doing R1 into R1, R1 into R2. Huh?
it is just same. If you do the multiplication, that is what you will get. Okay.
Is it this? I mean, is it applicable for any multiplication?
Yes, it is applicable.
Okay.
If it is A transpose.
Yeah, if it is A transpose.
What did you say? R1 into?
R1. This is R1 into R1. This is R1 into R2. This is R1 into R3. The same R3 into R1, R2 into R2 and all. Okay. And this last one is R3 dot R3. So what is R3 dot R3? It is 9 plus 36 plus 25. Okay.
So these R's you've taken this time as columns, right?
Yeah.
This time R1, R2, R3 taken as columns, right?
They are rows here.
They are rows here, and you have taken a transpose now. The transpose.
Yeah, this is the transpose. So this is your A and this is the transpose.
Okay. You were mentioning something about columns also in between, right? Do we have to column multiplication also in this case to find out whether they are orthogonal or not?
What I was saying, some student asked if A transpose is equal to identity, will the matrix be orthogonal? I said no. Here the columns are not orthogonal. For example, you check 1 into -2, 2 into 1, and 3 into -6. You do the dot product of these two columns, they are not orthogonal. So the columns are not orthogonal. For an orthogonal matrix, the columns are also orthogonal. Okay.
Okay, the rows and columns both have to be
yes.
0.
Orthogonal.
Orthogonal. Okay.
Orthogonal or orthonormal?
Yeah, and in fact they are orthonormal. Okay, which of the following options is or true? Let A and B be orthogonal matrices of order 3. Then A and B are equivalent matrices. Actually, we have not. This question should be coming after orthogonal matrices. Okay, so we will look at this projection first of all. So what is projection? You know that if you have two vectors A and B is projected along the vector A, then B is inner product A comma B by inner product A comma A into A. Okay, we have did the derivation in our lecture, so please refer to that for this derivation. And the general formula for projection of a vector onto a subspace is projection of V onto W is sigma I equal to 1 to n inner product V comma Vi into Vi. So this is the projection formula given you are having a orthonormal basis V1, V2, Vn. Okay. Note that it is an orthonormal basis. So you have norm Vi is equal to 1 for all I. Okay. Fine. So actually after completing this only I noticed that the same example we have done in the class lecture as well. So should I repeat it here?
No, ma'am.
Yeah.
Can you please explain the concept of this vector onto a subspace in short?
Which one, ma?
Projection of a vector onto a subspace.
See, projection of a vector onto a subspace means, so for example, here a vector is projected along a line. So instead of this, suppose you are having a 3-dimensional space, okay, and you are having maybe the XY plane, okay, and this is some vector outside the XY plane, and you want to project it on the XY plane, okay. So then, for example, this is something like 1, 2, 1. Then this here you will get 1, 2, 0. So this is the projection. So in this case, it is simply the XY plane. So you easily know what is the projection. But if it is some other different plane, then finding this projection is not very easy. That is why we have a formula like this, which gives us what is the projection of this vector on some subspace. It can be any dimension. The subspace can be of any dimension. Okay, fine.
So we'll find the basis for that subspace, and we'll find the projection in that basis.
Yes, exactly. So here, as I told you, this example I have done in the class lecture as well. Should I repeat this?
Yes, ma'am.
Okay, fine. We'll quickly do it. Okay. So fine. Here an inner product is given to you that x is equal to 1, 2. Find the projection of x in the direction of 3, 4 using the inner product defined above. So you are having here a vector x is equal to 1, 2, and you want to find the projection in the direction of 3, 4. So it means you are having only one vector 3, 4, and you want to find the projection of 1, 2 on this vector. So what is the space you are considering? Or here it is just only one vector, so you can easily use this formula also. Projection of B onto A. Okay, so this is the projection of B onto A. So projection of B onto A is given by inner product A comma B by inner product A comma A into A. So here your A is 1, 2 and B is 3, 4. So what is inner product A comma B with respect to this inner product?
B minus 4.
So 3 minus 4 minus 6 plus 4 4 is 16 and then 32, right?
25.
So you have 25. Is this fine?
Yes, sir.
And what is inner product A comma A with respect to this inner product? So 1, 2, 1, 2. So 1 minus 2 plus 16, right? So which is 13, right?
12, madam.
Yeah.
Oh, yeah, 13, 17 minus 13.
Did I make any mistake?
No. 13.
Yeah. So next you have to just do 25 by 13 into
1
your
by
A
2.
is
1
1.
and 2.
Okay. Now the next question is projection of x in a direction perpendicular to 3, 4. So you have
How
to
much
first.
the answer is different, ma'am, in the activity?
What is the answer given to you? Maybe I did some calculation error.
Here, I mean, one question here. So,
Projection of
yeah.
1, 2 on 3, 4.
Okay, just let me check what is the error I have done here.
I mean, one question here. Projection of B onto A, right? So here, is B 1, 2
Oh,
or
I
B?
switched the A and B.
Yeah.
Yes,
Okay.
ma'am.
Projection. So okay. So instead of taking okay, fine. So here I have to take this as the B and this is your A, right? Sorry. So then you know what is the calculation, right? I guess I don't have to repeat the calculation. Anyway, A dot B is the same. I can finish it quickly. No issues. So A dot B is going to be the same, 25. So just inner product A comma A is going to be different. So it is 3 3s are 9 minus 24 plus 4 times of
49.
not 49, 16.
Total answer 49.
Yeah, 49. Okay, 49 into 3. Okay, this is the answer, right? Sorry, here I switched the A and B. Okay. Let x is equal to 1, 2. Find the projection of x is in a direction perpendicular to 3, 4. Perpendicular to 3, 4 means.
The answer is given as 11, 25, 3, 4.
11,
25 and 3, 4, ma'am. Sorry, 11 by 25 into 3, 4.
No, this answer is correct. For which one you are saying? The next one is maybe
A
this.
only, ma'am. The answer in activity question, it is given as 11 by 25 into 3, 4.
I don't think so. This answer is correct.
I think that's for the next question, the perpendicular question.
Yeah.
Okay, this answer is correct.
Just check. Let us wait for the B section to complete.
Okay.
Maybe that was the normal or what?
If it's 25, then it will be like normal.
Yeah.
Okay. So here you are given that it is perpendicular with respect to this inner product. Okay. So with respect to this, it is 0 means what is that equation you are getting? First of all, we need to find that. So 3x1 minus 3x2 minus 4x1 plus 16 x2 is equal to 0, right? It means what? You are getting minus x1 plus 13 x2 is equal to 0, right? So if I am taking x2 is equal to 1, then what is your x1?
13.
13. So your vector is 13 comma along the direction 13 comma 1. So it means what? Your B is still 1 comma 2 and your A is 13 comma 1. Okay. Now you have to again use the same formula, projection of B onto A. Okay. So here inner product A comma B by inner product A comma A into A. You want me to complete this one? These calculations?
It's okay, madam.
Okay, please do this inner product calculations by yourself. Okay.
Okay.
So here you will get some scalar. For that scalar you need to find into 13 comma 1. Okay. Fine. Now consider an orthogonal basis of a subspace W. Suppose you are given a basis for a subspace and you are asked to find what is the projection of any other vector onto this particular subspace. Already here in this case the basis is given. Suppose the basis is not given, then the first step will be to find a basis. Okay. So what is the projection of W on Y you need to find? Sorry, projection of Y on W you need to find. You need an orthonormal basis. Please remember that. So since here, first of all, you need to verify, is this orthogonal? Is this orthogonal?
Orthogonal.
Yes, yes, ma'am.
It is orthogonal, but they are not orthonormal. So to normalize it, we have to divide it by its norm. Right?
Correct, madam.
So you have 1 by square root of
6
into 1 comma 2 comma 1, and your U2 is
8
1 by square root of 8 into minus 2 comma 0 comma 2. Okay. Now you have, this is the orthonormal basis you are having. U1, U2 is your orthonormal basis. Now how to find the projection of your Y onto W? What is the formula? Summation, or straight away let us write. So what is the formula? Inner product V comma Vi into Vi. So here your 1 comma 2 comma 3 into your U1, which is
minus
1 by root 6. So let us keep this 1 by root 6 outside, into 1 comma 2 comma 1 plus 1 comma 2 comma 3. Sorry, here I missed something. Into V1, right? Or I put the bracket in this way. Inner product V comma Vi into Vi, right? So 1 comma 2 comma 1.
2
So
comma
there are 6 then. So it will become 6, right?
Yes.
And then 1 by 8, 1 comma 2 comma 3 minus 2 comma 0 comma 2 into minus 2 comma 0 comma 2. So you have 1 by 6 times. What is the inner product? 1 plus 4 plus 3, 8, right? So when you might multiply 8 inside, what will you get? Or you can
8.
keep it also, so that you can simplify first and then multiply. And here minus 2 plus 6. So you have 4 by 8.
We'll do the calculations.
Okay. So this you can complete and you get the answer. Fine.
Madam, how did you got this under root for 6 got over? Because it was multiplied by vector V1, right?
Yeah, here what happens?
V1 is orthogonal basis V1.
Yeah.
Right?
Yeah, so this is your U1, this is your U1. So here you have a root 6 and here you have a root 6. Root 6 into root 6 I have taken outside, that's all.
Small confusion, madam. You said you have a formula which is summation I to N.
The formula only I have used here. Summation, I maybe this color. Summation inner product v comma vi into vi I equal to 1 to n. This is the formula we have given here. We are given here.
Correct.
So now here your v is nothing but your y, and instead of vi's you are having ui's.
Okay. Perfect.
Okay.
Yeah.
Ma'am, if the basis is not given, how do you find? Just quickly, if you can.
See, for example, whenever you are given a subspace, how do you find the basis? I guess we have done some example here also. Somewhere I have even if you are given a subspace, how to find a basis, I don't know. Maybe quickly I'll tell. If a plane is given, how do you find a basis? So suppose you are given a plane like this, x plus y plus z is equal to 0. Suppose this is the plane. So you obviously you see that this is a plane. Then what is the dimension of a plane?
2.
So then you can find just put z is equal to 1 and y is equal to 0. Then what is your x value?
-1.
Okay. Now same way you can put y is equal to 1 and z is equal to 0. Then again your x is
-1.
-1 still, right? So you have -1, 0, 1 and -1, 1, 0. So this forms a basis. So in this way you can form a basis if that the subspace is given. So here the subspace is set of all x comma y comma z such that x plus y plus z equal to 0. Okay, if a subspace is given like this, then you form a basis in this way. Try to use only zeros and ones. Okay, so that you have a simpler basis. So the conversion into an orthonormal basis is easier. Okay.
Got it. Yeah. Thank you.
Okay. Where were we? Yeah. So the next topic is projection as a linear transformation. So let V be an inner product space and W be a subspace. Define T from V to V defined by T of V equal to projection of V onto W. Then this defines a linear transformation. This we have already verified that it is a linear transformation. And what is the range of T? Where is it projected to?
W.
Right? And what is the rank of T?
Dimension of W.
And what is the kernel of T?
Some
Yeah, it's the
W pub, yeah.
right. It is a set of all vectors V in V such that inner product V comma W is 0. Okay, that is the kernel of W. Okay.
Ma'am, for what is T here, ma'am? Is it a linear transformation?
Yes. It is given that T is a linear transformation and it is defined in this way.
Okay, for such kind of a transformation, these are true, ma'am?
Yes.
Only for transformation which is equal to the projection, ma'am?
Yes, exactly. Okay. Fine. And this particular set is called the orthogonal complement of W. Okay, and it is precisely the kernel of this transformation. And for such transformation, the another important property is that T squared is equal to T. Okay, and PW of V, the norm is less than or equal to norm of V. The projection of a vector cannot be longer than the vector itself. Okay, this I have explained
Where
already.
did we get W, ma'am, in the above thing? In the transformation, W.
The W is the subspace. The projection on which it is the projection on the particular subspace W. Okay, so here your PWT is nothing but PW. Just the notation. Projection on the space W. Okay.
Okay.
Okay. Let V be a plane spanned by the vectors V1 and V2. How do you find V perp? What is the
You
definition?
just take a vector x, y, z, v is equals to x, y, z, and take inner product it and equals to 0.
Yeah. So you have to see that inner product x comma V1 equal to 0 and inner product x comma V2, or I call this U maybe. Some vector U. So this is your U comma V2 is 0. Okay. So now it means what? X comma Y comma Z. So U dot V. What is U dot? Let us consider the usual inner product because no specific inner product is mentioned means you consider the usual inner product. So what is u dot v1? So this is your u. What is u dot v1? X plus y is 0. Sorry?
X plus y is 0. That's fine.
Can you please be louder?
Actually, the same thing, madam. X plus y equals 0. I was just taking along with you.
Okay. So x plus y is equal to 0 and y plus z is equal to 0. Right? Okay. So x plus y is equal to 0 and y plus z is equal to 0. This is the system you need to consider. So now from this, what is the vector which satisfies this condition? If you take y to be some t, then your x is minus t, your z is also minus t. Okay. So your v purpose set of all minus t, comma minus t such that your t is in R.
Mom, can you explain it again, Mom? I didn't understand.
This part or from the beginning?
From the beginning, Mom.
See, now what is the definition of the perpendicular, the orthogonal complement? The set of all v in v such that the inner product with all the vectors in this subspace W is 0. Okay, so here the subspace V is the span of V1, V2. So this V1 and V2 is forming a basis for this V. So instead of just finding, instead of taking any element V in V and saying inner product W comma V is equal to 0, what I am doing is that I am just taking the basis elements and considering the inner product to be 0 with these basis elements. That is sufficient instead of doing the entire subspace itself. Okay. So here what in the definition can be said that suppose W, you have a basis W1, W2, Wk. Okay, this is a basis for W. Then this definition is equivalently set of all V in V such that inner product V comma Wi is equal to 0 for all I in 1 to k. Okay, this is an equivalent definition which I have used here. Okay, now is it fine?
Mom, and the next steps, what did you do, Mom? U comma V.
So here you see that this vector I am calling it as a general vector is u. So I am just considering u dot v1. We already know it is 0. So u is x comma y comma z. Dot product with v1 I get x plus y. And u with dot product with v2 I get y plus z. And you know that it is equal to 0. And then you consider this system of equation.
How did we get x plus y, Mom?
What is dot product of this vector with this vector?
Why are we considering x comma? Okay, you just took a random vector and then you're just doing the dot product. Okay.
Now solving this, you will get this. That's all. Okay.
Thank you.
Okay. So now look at this question. Let this inner product denote the standard inner product on R2. Now inner product x1 comma x2 into inner product y1 comma y2 is the usual inner product. Okay. Now W1 is this space and W2 is this space. So what is the perp of these two subspaces you are asked to find? So first of all, let's rewrite what is your W1. It is the set of all x comma 2x, right? Your y is simply 2x. And what is W2? It is a set of all x comma minus 2x. Now take an arbitrary vector. Let us say u comma v. And what is this u comma v dot x comma 2x? What does this give? What does this give?
Ux plus 2vx is equals to 0.
Okay, so it means what? U plus 2v times x is 0. Okay, so it means you have u plus 2v equal to 0. It means you have u is equal to minus 2v. Okay, so u is equal to minus 2v means, so the first coordinate is u, second coordinate is, or either way around. So I'll write v in terms of u
minus u.
Or directly we'll look at the answer and verify. So you need to have 2y is equal to minus x. So this option coincides, right? W1 perp.
We can go with the equation of line also, right? 90 degrees, like just the slope thing.
Yeah, so here you have 2v is equal to minus u. So your u is the first coordinate and v is equal to v is the second coordinate. So you see this option matches with this. I have not skipped any equation here. So is the steps clear for everyone?
Correct.
Yes.
So you have found what is W1. For W2, you take this element and multiply it with an arbitrary vector x comma minus 2x. You multiply. So now what is this giving you? Ux minus 2vx is 0. So u minus 2v times x is 0. It means u minus 2v. Okay. So you see that you have got W2 purpose 2v equal to x. This is how you need to find the orthogonal complement. Okay.
Yes, sir.
Which all these vectors are perpendicular to W.
Yeah, exactly.
So can you show
All the vectors perpendicular to a given subspace gives the orthogonal complement of a subspace. Okay, fine. This Gram-Schmidt process I have just given how to find it. I have not given an example because doing all this process is going to take some time. So I did not add any example for this Gram-Schmidt alone. So Gram-Schmidt, what is that we are doing? I'll just recall it quickly and then I'll move on. So for Gram-Schmidt, given any ordered basis of a vector space, how to convert it into an orthonormal basis. Okay, the steps are as follows. So you take first W1 is equal to V1 and then normalize it. Okay, and then for W2, W3 and so on, the general formula is Vi minus sigma j equal to I minus 1, inner product Vi with Uj, and then Ui is simply this Wi by norm Wi. So this is the formula you need to remember for using this Gram-Schmidt process. I have not given an example. So please refer to our usual session for this example I have given there. Okay. So from this, we know that any finite dimensional inner product space has an orthonormal basis. Okay. Fine. So the next concept is what is an orthogonal transformation. Okay. So for orthogonal transformation, the linear transformation, first of all, is called orthogonal if this condition is satisfied. What is this condition? Inner product TV comma TW is equal to inner product V comma W. Okay, that is an orthogonal transformation preserves the inner product. Okay, so it means preserving the inner product means what happens? What happens if you are considering the usual dot product? You know that the length and angles are preserved. Okay, remember this property that the length and angles are preserved when you are considering a dot product. Okay, but before this, I guess I have stopped some problems because I wanted to first cover the theory part. Oh yeah, I have to first complete this part and then come back. Yeah, okay, fine. I'll finish this. Okay, fine. So this is an orthogonal transformation. Remember this property. This I don't know how to highlight. Remember, this is something important. Okay.
Ma'am, there was this one question where they asked to find out if it is an orthogonal transformation or not. Can you just show, ma'am, like one example of if it is an orthogonal transformation?
Yeah, we'll do that. We'll do that. Okay. So and then what are orthogonal matrices? Orthogonal matrices are matrices with respect to an orthogonal linear transformation. Okay. So it satisfies this condition that A transpose A is equal to A transpose A. Sorry, A transpose equal to A transpose A equal to identity. Remember that rows of matrix are orthonormal implies A transpose equal to identity. This is an if and only if condition. Same way, you know that columns are orthonormal if A transpose A equal to identity. This is also an if and only if condition. So only when both the rows and columns are orthogonal, then only you know that it forms a orthogonal matrix. And the corresponding linear transformation is orthogonal. Okay. So now let us look at this question. Let V be in R3 be a vector such that norm V is equal to 5. If u is the vector obtained from V after an anti-clockwise rotation of xy plane with angle 70 degree about the z-axis, find the length of the vector u. So what happens to the rotation? Rotation means, so you are having some vector, you are just going to move it to some other direction. So the vector, the length of this vector is just going to remain the same. Is it or not? Whatever angle you are rotating, the length is going to remain the same. Okay. So remember, rotation matrices. Rotation matrices are examples of orthogonal matrices. Okay. And here what they are saying is that if you are doing this anti-clockwise rotation, you are actually multiplying a rotation matrix with V. Okay. So here rotation matrices, you know that they are orthogonal. Orthogonal means you know that they preserve, what is the property I told? They preserve the length and angle. Okay. They preserve the length and angle. It means what? If a vector V is shifted to, rotated to 70 degree, what is the length of U then?
5. Sir.
5.
It is going to be 5 because the length is preserved. Length is preserved means this is the length of the vectors. So they are preserved when rotated. So the norms are same. Is it fine?
And how angle are preserved?
Okay. Fine.
And how angle?
Sorry? Okay. Let the matrix of a linear transformation T from R3 to R3 is given in this way. So this is your matrix U. And B is this matrix. So now choose the correct statement. T is the orthogonal transformation. So if you are given a transformation like this with respect to a matrix, then it is actually easier to verify whether it is orthogonal. You simply have to check whether the rows and columns are orthonormal. Okay, first of all, are they orthonormal? First of all, they are normal vector. I mean, are they unit vectors? Each of them? Yes, right?
You will multiply each inner product of each rows and columns, right?
Yeah. So if you are taking R1, R2 or R3 or C1, C2, C3, in any way if you take, you see that Ri, Rj is 0 if I not equal to j and equal to 1 if I equal to j.
Ma'am, is it always the case where rows are orthonormal and then columns are also orthonormal?
No, only when it is orthogonal, then only it is true. You
Like
have seen,
both of them at the same time, are they orthonormal? No?
yes,
Or
here
it
for
depends.
orthogonal matrix, that is the property, right?
Okay. Like if only rows are orthonormal, then it doesn't form the orthogonal.
Yes. I have given an example also. We have discussed it. Just before a few slides, we have discussed it. Okay. Fine. So here you see that this matrix satisfies all this property. Okay. So Ri dot Rj is 0 for all I not equal to j. This condition tells that the rows are orthogonal. Orthogonal. Rows are orthogonal. Same way this condition, first condition says that it is orthogonal. And what about the second condition, I equal to j? I equal to j says that each of these rows is having norm 1. Same way, each of this column is having norm 1. Okay. So you see that this matrix has all the rows are orthogonal as well, orthonormal, as well as the columns are orthonormal. So does this T is form an orthogonal transformation?
Yes.
Yes. Okay. B is a real symmetric matrix. What is mean by a symmetric matrix?
B transpose
to B.
So it means what? Bij should be equal to Bji. So you see, this is a symmetric matrix, right?
Correct.
Okay. Now, for an orthogonal matrix, what is the property we have? AA transpose equal to A transpose A
Transpose A
into
equals
I.
1 3.
So what is the inverse of this matrix?
A transpose.
Here it is U. So what is U inverse?
U transpose.
It is simply U transpose. Okay. It is simply U transpose. So you don't have to worry about when you are finding this, how to find U inverse, you don't have to worry. It is an orthogonal matrix, so you know U inverse is simply U transpose. Okay. Okay, fine. I guess you have to do this verification that U transpose B times of U. What is the answer? You can calculate it and check it. Okay. Or should I do the calculation?
Multiplication of matrices, right?
Yeah, it is just multiplication of matrices.
No problem. We'll do that.
Okay, please verify that. All right. So let me go back to this problem here. Yeah. So let A and B be orthogonal matrices of order 3. Then A and B are equivalent matrices. Is that true? Yes.
Yes, ma'am. Rank.
What is the property about orthogonal matrices? Yeah. Rank of A. What is rank of A and rank of B for orthogonal matrix? It is full rank, right? Because the columns and rows are linearly independent.
Correct.
So it is full rank. So the ranks are equal. So they are equivalent matrices, right?
Yeah.
That's right.
Okay. Let A and B are orthogonal matrices. Then A and B are similar matrices. Is this possible?
Not sure, madam.
See, for example, you consider this as well as this. Both are orthogonal actually. Okay. Both are orthogonal. But you see they are not similar. Okay. So this is for option 2. So you see these two matrices are orthogonal, but they are not similar. So this is incorrect. Let A be a rotation matrix corresponding to the anti-clockwise rotation of the xy plane about the z-axis with angle theta. The nullity of the matrix A is zero. What I told you about the rotation matrix. Rotation matrices are
orthogonal matrix.
They are orthogonal matrix. So orthogonal matrix, you know that they are invertible. Yeah. So then, what about the nullity of them?
Zero.
Zero, right? So it is correct. Okay. Fine. Let A be a rotation matrix. Yeah.
Ma'am, every rotation matrices are orthogonal. Okay.
Okay. Let A be a rotation matrix corresponding to the anti-clockwise rotation of the xy plane about the z-axis with angle theta. And B be the rotation matrix corresponding to the anti-clockwise rotation of the yz plane about the x-axis with angle beta. Then A and B are equivalent matrices.
They have same rank.
Yeah, the argument is exactly same like the option 1. Both are rotation matrices, so they are orthogonal. So it means they are full rank. So their ranks are equal. So if the ranks are equal, then they are going to be equivalent matrices. Is that fine?
Is the axis difference in axis and angle would not affect here, right, madam?
Nothing is going to affect the rank. If they are rotation matrices, they are orthogonal. Orthogonal means full rank.
Okay.
Okay. Okay. Fine. There was one more problem which I left halfway.
Yeah, that was a projection, madam, I guess.
Yeah.
Yeah,
So if PW denotes the linear transformation which projects the vectors of an inner product V to a subspace W of V, then range of PW intersection null space of PW is singleton 0. Is that true? Okay. So in this case, I want to mention a fact here. W intersection W perp is always singleton 0. Why is that? Why is that so? What? Let us say you have some vector V in W intersection W perp. Okay. What is the definition of W perp? W perp means inner product V comma W is equal to 0 for all V in W. Right? Or set of all V in W. This is your W perp such that for all W in W. So this is the definition. Now, if your V is in W also, okay, V is in a W as well as W perp, it means your inner product V comma V itself is 0. So this is possible only when
V equal to 0, but here it's not certain.
Okay, so it means the intersection can have only the 0 vector.
One column element, common element, that is 0.
Ma'am,
Sorry?
please explain it again.
Common element 0, which is the intersection of
Yeah. The common element in W and W perp is 0. So if that means what I'm taking any arbitrary element from this intersection, then what I'm proving is that this is the definition of W perp. Now, according to this definition, in this V is also in W, right? So in place of W, I'm putting V. Okay. So what I get, inner product V comma V is 0. Okay. So it means V is 0. So the common element in V and V perp is only the 0 vector. Now for PW, what is the range of PW?
Dimension.
And what is the null space of PW?
VW perp.
The W perp. So W perp, W intersection W perp is
0.
0.
Single time 0.
Okay, fine. And what about option 4?
Option 3 is right, correct?
Yeah, it's true.
Yeah, option
Square
3.
will be 0.
Ma'am, how to go for option 4?
Option
Square
4,
will be-
suppose it's a projection, then what is the property of the projection? You know, P squared is equal to P. So you have to just verify whether this matrix satisfies this condition.
Okay.
So what about, do I have space? I don't have space. Okay, let me do it here. Okay. So what is 1 minus 1, 0, 1 into 1 minus 1, 0, 1? It is 1. And then here it becomes 1 into minus 1. This is 0. And this is also 0. And this is 1. Right? So the square is not the same matrix. So this cannot be a projection. So correct, right? Okay.
Can you explain option 1 once again?
Option 1. Yeah, sure. See, option 1, either you look at this way or this way is actually very straightforward. Maybe I use this. Or see, inner product V comma Vi is equal to 0 for all I. It means here your V is some element of your vector space V, and this is a basis. So I'm writing first of all this V as a linear combination of your alpha I and Vi. Now your alpha I, okay, so now you see alpha is simply inner product V comma Vi, or you expand this, you will get it. So what is that you are getting? Alpha I's are simply inner product V comma Vi. So it means V comma Vi's are all 0 already is given. So your alpha I's are 0 means your V becomes 0, right? Is that fine? Yes or no? Should I explain again?
Yes, I'm fine.
See, V is the linear combination of all Vi's. So alpha I know by this property that I can write it in this way, inner product V comma Vi. So alpha I is inner product V comma Vi, which is already 0. And so if all the alphas are 0, then you know V is 0. Okay, that's all. Okay, so and there was one question from the previous session which you all wanted me to do. Where was this question? I have already solved it here. So let T be a linear transformation from R3. I guess this was the question you asked, right?
Yes, ma'am. This was the question.
Yeah. So let T be a linear transformation from R3 to R2 defined as T of X comma Y comma Z in this way. Now A be the matrix representation of T with respect to some other basis for domain and for codomain. A is given in this format. You are asked to find the null space, and they have given a specific format for null space. This is important here. Okay. So here, what is that you are doing? First of all, you are finding this matrix. Okay. How do you find the matrix? The usual way. You consider what is T of this basis elements and express this images in terms of this basis element. Okay. So you get the matrix. Once you get the matrix, what do? You find, so now what is your T of X comma Y comma Z? Your T of X comma Y comma Z is X plus Y minus Z, Y plus Z. So now these two terms are going to become 0 for the null space. Okay, so this is your null space. So your null space T of
why
x
is
comma
it
y
the
comma
null
z.
space, ma'am?
Yeah.
Are we considering
What
it
is the
by
definition of null space? Set of
it is a
all V in
solution?
R3 such that T V equal to 0, right?
Yes, ma'am. In the
That is what I have
question,
done.
okay, can you once show the question, ma'am? I still didn't understand why is it okay. They asked you to take SB the null space of T. Okay.
Yeah, I'm coming to it next. Okay. Fine. So now, according to the definition, this is the null space. Okay. And from this, you get that z is equal to x plus y and z is equal to minus y. Now, from from this, again, you write z is equal to minus y means, so when I substitute it here, z is equal to minus y, you get x is equal to 2z. Okay. So here you get that x is equal to 2z because x is equal, y I'm writing as minus z. So x minus z is equal to z. So x is equal to 2z. Is that fine? This 2 together gives this. Is this fine? And I'm writing y as minus z. So it means what? Your x is 2z, your y is minus z, and z I'm keeping it as such. Okay. So now this is the null space I'm getting. Why I have returned it in this format? Because here they have mentioned that I want to write x as mz and y as nz. So this format I'm using from the way they have given. So x is mz, they want to write it in this way. That's why I have considered it in this way, and I have given
where
what's
did we get the equations x plus y minus z is equal to 0?
I told you, right? That is the definition of T of x comma y comma z given to you. X plus y minus z plus z.
Okay.
Okay. And here you see that only z is the free variable. So the dimension of this space is 1. Okay. That's all.
Yeah,
And
ma'am.
for
Here was the question was we have given the transformation equation, but suppose we don't have the transformation equation, we just have this matrix. Then how can we find that for this? Like,
okay, then in that case, what you need to do is that you have to find the transformation first of all and do the null space. That's all.
yeah, like the transformation also given and the matrix also given. Now how can we find the null space? That was our question.
See, if the matrix is given to you, see here in this case you were finding the matrix. If the matrix is given to you, then you can simply find the okay. So suppose let's say this is the matrix given to you, and you want to find the null space corresponding to T. Then first of all, you find what is your T of x comma y comma z. Using this matrix, you find it. You are asking that only, right? If the transformation is not
Yeah.
given, then what to do, right?
Transformation equation not given, but a transformation like 1 1 0 is 2 1. This is given, and the matrix you will find from that.
Yeah, that is
Now,
what I'm saying. In that case, suppose only this is given. From this, you first of all find what is T of x comma y comma z. I have already given examples, right? Suppose you know the images of the basis element, you can find the transformation explicitly. How? Because you can express x comma y comma z as alpha times of 1 1 0 plus beta times of 0 1 1 plus gamma times of 1 0 1. So now alpha, beta, gamma, you find the solution in terms of x, y, z.
so from that we can get the equation from that.
That's all.
But there was a method of that, like we can find out the like null space from that matrix also. We will
Yes,
put
you can find it from the matrix also.
like we will.
But your method
find,
is most easier, it seems.
Yeah,
man. Like
yeah.
the one the TA gave was like we reduce the matrix and we get the null space from it. Then we represent that.
We have to represent that
linear combination of that whatever like the non-standard basis for that domain.
For the code, for the domain, yes, we have to represent in that. If we do by row reduce from, then we have to represent from that from
See, there are
codomain.
several ways to do one problem, right? So
But
yeah,
this is easy. This is easy.
You use whatever is convenient for you.
Okay, ma'am. Thank you. Thank you very much.
Okay, so I have tried to cover almost all the topics during the revision session. Hope it is useful for you. So all the best for your quiz then.
Ma'am, you will share this PDF?
Yes, immediately I will share. Okay. So yesterday's PDF only created some issue. Today I will share it immediately.
Thank you, ma'am.
Yeah, ma'am, please
Madam,
just now send
where
it.
would I find this?
Sorry?
Where would I find this?